When we look at the graph of the tangent function, it's helpful to remember what we divide to get the tangent function. What goes into what in terms of the tangent? Tangent is sine of x divided by cosine of x. Excellent. So this function is going to have problems exactly where the cosine have problems. So the question is, where does the cosine of x equal 0? We've already discussed that. Cosine of x equals 0. That was the harder one. Does anyone got that? What values could x equal? How about odd multiples of pi over 2? It was that one, the ugly one. All right. So if you use the link that I gave you on Desmos, then we can look at the graph of the tangent function. Now, the graph of the tangent function is going to be defined just like the graph of the secant, where the cosine is 0. So let's click this. That's where your vertical asymptotes are going to be. Hopefully you should see that those are odd multiples of pi over 2. Now, if you want to see what the rest of the graph looks like, then slowly drag the slider. I'm going to see a shape that repeats itself. It goes through the x-axis in the middle of those asymptotes and has kind of a cubic look to its graph, a little bit of a graph of a cubic, but there's your graph of the tangent function. So it's a nice periodic function. In fact, if you look at it, the distance between where it repeats is just pi. So that's a little different than your sine and cosine functions and your secant and cosecant functions, which all have a period of 2 pi. Here the period is pi. So, okay, great, great. Let's take a look at something else here with regard to the graph of the tangent function. What if I had a number in front of the tangent other than just a 1, say? Now, to appreciate the difference here, what I'm going to ask you to do, if you're following along with this link, is turn on this other graph here, and then let's change the value of b. Let's make it bigger. So click and drag the slider to the right, and what you should see is your graph being stretched and stretched further away from the x-axis. So you're stretching it away, it's making it taller. Now, you could also dial it down and go the other direction. You could make it smaller, or if you made it negative, once we cross 0, bam, you're getting a nice little flip. You've reflected it across the x-axis. So there's a lot of different shape you could give to this, but the basic shape is kind of like this. And just like the graph of the secant and cosecant, what really defines this graph is where are the vertical asymptotes. So once again, it's helpful to know that cosine of x equals 0 right here. Okay. With this in mind, let's take a look at problem number 18. And this is really getting to something I wouldn't really expect you to be able to draw freehand, and that is the difference between the graph of minus a tangent and minus 2 times a tangent. I don't really expect you to be able to tell me or show me the exact difference between those, but if I had these labeled, yeah, you should be able to figure out which one is which. Let's start by looking at the graph of minus the tangent. So, okay, if I can find my Desmos link, there we go. So that would be when b is equal to -1. So I'll move that over to -1. Let me just shut this, this part of it off for a second. And then try and appreciate, well, what's going to happen? That's not -1. There. Oh, I shut off the wrong one. All right, my bad. There we go. I wanted to shut off this one and keep on the top one. So there is a graph of the tangent at -1. Let's compare that to what happens when we look at -2. Well, what's going to happen at -2 is this is going to get stretched farther away from the x-axis. So, like that. So what you're going to need to do is kind of use your imagination a little bit, or you can graph both functions at once on whatever medium you want, and try and decide which one's which. Which one's the tangent, which one's negative the tangent, which one's -2 times the tangent. And what's happening is that each of these points, when you're going from negative the tangent to -2 times the tangent, is getting stretched a little farther away from the x-axis. So there, and then there. And the remaining one would be here. So it's not stretched as far, but that coefficient stretches it away from the x-axis. The asymptotes here are going to be the same as they were for the graph of the tangent, and those are going to be exactly where cosine of x equals 0. So the first one is when x equals pi over 2, and then this over under here is going to be x equals -pi over 2. Moving out, if you wanted to figure out where the next one would be, that's going to be kind of way out here. That next one would be x equals 3pi over 2. Again, just odd multiples of pi over 2. But the big thing in this first one is just to try and distinguish between these two graphs. You know, if I gave you both of them, you should be able to label which one's which. All right, nice. But let's work on a little bit more challenging one, the graph of the tangent of x over 2. Before I get there, maybe I should take note of the domain and the range. Domain is everything except these values. So it's x not equal to 2n plus 1 over 2 times pi. It's everything except those. The range is a little different. It's actually a lot different. Does anyone want to take a poke at the range? Where does the range go? What's the lowest value of x or lowest value of y you think this graph gets to? Yeah, excellent, -infinity. Well done. And the upper limit would be, yeah, so -infinity to infinity. Now I'll give you a little chance for some extra credit. If on a test you run into this answer -infinity to infinity, and instead of that you write script r, woohoo, that's a bonus point. I like that. Script r just really means all real numbers. It's just something that I picked up in graduate school or undergrad or someplace, but I always kind of like that notation. I think it's kind of convenient. So, oh, you know what? In my math lab, you're going to be entering it like this. So if you do this, I really don't have a preference. I'm just offering you a chance of extra credit if you use it in the appropriate way. Now, I always got to caution myself to say if you use it in the appropriate way, because I remember having a student write script R on every single problem of her test, and she wanted extra credit on every single one of them. I'm like, well, that's not exactly how it works. So, all right. So cool. We got the domain and the range all set. All set. Questions or comments on that one before I move on? All right. Well, let's continue with problem number 22 and the graph of the tangent of x over 2. So problem 22. Y equals tangent of x over 2. Now, realistically, if you want to try and dissect this problem a little bit, tangent is still sine over cosine. It's just that in this case, it's sine of x over 2 divided by cosine of x over 2. Okay. We still got to worry about the denominator equaling 0. So the question is, where does cosine of x over 2 equal 0? Okay, well, that's a good question. Let's see if we can't find out. We know where cosine of x equals 0. Cosine of x equals 0 right here. So basically I want to know where does x over 2 equal 2n plus 1 over 2 times pi. I got to solve this for x. Now it might look a little bit on the ugly side, but realistically, this is going to be one of the quicker problems like this we'll solve. 2n plus 1, 2 times pi. What do I have to do to get x by itself here? Yep, multiply both sides by 2. So, nice. So if I multiply both sides by 2, the 2's on the left-hand side cancel, and the 2's on the right-hand side cancel, and I'm left with x equals 2n plus 1 times pi. Now maybe you're getting used to seeing this, maybe not. So let me just point out again. Let's plug in some different values for x. Negative 2, negative 1, 0, 1, and 2. I said x, I meant n. If I plug in n equals 0, I get 1 times pi, or just pi. If I plug in n equal 1, I get 3 times pi, 5 times pi, negative pi, negative 3 pi. The thing to keep in mind about this is 2n plus 1, that's going to be an odd number. Always. When you're talking about n as an integer, 2n plus 1 is going to be an odd number. So basically what you've got are odd multiples of pi. 1 pi, 3 pi, 5 pi, etc. So that's where you're going to have your vertical asymptotes. The rest of it is drawing the right shape in between those vertical asymptotes. So let's go over to our graph. We can label these asymptotes. X equal pi, x equal 3 pi, x equal negative pi, and x equal negative 3 pi. Now maybe it's not a bad idea to take out your graphing calculator and take a look at it as well. And just for the practice here, I'll do that. So the good news for us is that we don't have to worry about being fancy with the denominators. We can just type in the function. It's going to be tangent of x divided by 2. Now let me set up the window. I'm going to go from negative 3 pi to 3 pi. And then I'm going to put tick marks every pi units. On the x-axis, let me continue to work with Anthony's suggestion of negative 10 to 10. And since I'm in radian mode, I think I should be good to go for the graph. So let's see what it looks like. Bam, there you go. I got a total of 3 periods of this graph. Now the problem only asks you for 2, but that's okay. Notice that this graph has its x-intercept right between the vertical asymptotes. Now it would take a heroic effort to get your graphing calculator to graph the vertical asymptotes. Don't bother with it, but just know that they're there. That's a feature that I'm going to want to see on your exams. So these are your vertical asymptotes. You've labeled them for me very nicely. That's good. Last but not least, let's just try and draw a reasonable looking tangent function. If you notice, I'm not really taking time to plot any points. The only one that I want you to get at least somewhat close to is the midpoint, because the graph's going to cross through that midpoint. Okay, so something like that. That's 2 periods of the graph. So if that's all I ask for, you'd be done. But for sake of completeness, let me just go through this one again. There. There's your tangent of pi over 2. But I hope I'm being clear that I want you to label these asymptotes and I want you to show me the calculation. How did you find where those are? There's nothing wrong with you labeling, or excuse me, using your graphing calculator, or if I allow you to use Desmos to double check it, that's fine. But you should be able to show me that calculation. The domain is everything except odd multiples of pi. So it's going to be x not equal to 2n plus 1 times pi. How about the range? What's the range going to equal? Yeah, all real numbers. Negative infinity to infinity, or my script R. Beautiful. All right. That part? Sure. So we're next going to look at the graph of the cotangent. And we'll do one of those. You good there? So I do believe I sent out a link in the chat earlier for the graph of the cotangent. We're going to go to that one now. Cotangent is going to be what over what in terms of your functions? Cosine over sine. So let's work on that a little bit. So y equals cotangent of x, so that's cosine of x over sine of x. We'll have vertical asymptotes when sine of x, oops, that's 6, how about sine of x equals 0? Has anyone got this one? Where does the sine function cross the x-axis? Where does sine of x equal 0? And pi. When x equals some multiple of pi. Perfect. Just any multiple, any integer multiple of pi. So if we turn our attention to problem 24, we've got y equals the cotangent of pi x over 4. And actually, before we get there, let's take a look at our Desmos link and play around with that for just a minute. And that's this one. So you just told me that with multiples of pi, that's where you're going to have vertical asymptotes. So let's put that in here. And then slowly but surely, let's trace out what the graph of the cotangent is going to look like. So if you grab that slider and move it to the left, you'll see the cotangent function kind of snaking its way in between your vertical asymptotes. And part of the reason I set this up like I did here is so that you could experience this graph a little bit more carefully, and also so that it really tries to highlight the fact that this graph is shaped by where the denominator is 0. So understanding that and finding those points is a big thing for us, making sure you know where the graph is 0. That gives you the vertical asymptotes. It also figures out your domain. So let's do that here. Let's figure out what that's going to mean for us. This is going to be cosine of pi x over 4 divided by sine of pi x over 4. where is that going to be 0? What values of x? So the denominator equals 0 when pi x over 4 equals n pi. This one actually solves pretty nice. We actually get some nice values out of it. So see if you can't solve for x. If you're watching this later at home sometime, pause the video, solve for x. Do a little table of values. Plug in values for n, get values for x. Try and predict where your vertical asymptotes are going to be. All right. So I muted everyone in case you need the chat. Just unmute yourself, that's fine, but somebody was coming in and out of a door, so. Okay. One more second here. -2, -1, 0, 1, and 2. Kind of like before, we'll multiply both sides by the reciprocal, which is 4 over pi times 4 over pi. On the left-hand side, everything cancels, leaving you with just 1 times x, or just x. On the right-hand side, units of pi cancels, and then we're left with 4 times n. If you then plug this in over here, -2 times 4 is -8, -4, 0, 1, 0, 4, and 8. Those are going to be your vertical asymptotes. If you downloaded the handout, then you might notice that unlike the previous problems, I don't have the asymptotes drawn for you. This is going to be what your test is going to be like. You're going to have to figure out where to put the asymptotes. So in this case, it's at 4 and 8, -4, -8. So let me just put those in here. Now sometimes I'll put them in with dashes, just to emphasize the fact that this is not really part of the graph. It's just a feature of the graph. But when you actually click on the graph on your graphing calculator or on Desmos, you're not going to see these lines perk up. Now the graph of the cotangent kind of looks opposite the graph of the tangent, in as much as tangent's increasing, cotangent's decreasing. Now the rest of this you can get by looking at it on your graphing calculator or on Desmos. Nice thing about Desmos is you can actually type in cotangent. So where do you want to do it? Want to do it on the graphing calculator or Desmos? It's up to you. Graphing calculator? All right, let's do it on the graphing calculator. So let me clear out a bunch of stuff here. Let's clear this out and clear this out. So on the graphing calculator, you've got two choices as to how you can input this function. So one of them is like the way we wrote it just a minute ago, cosine over sine. But there's another clever way that you could do this. Does anyone know a different way I could write the cotangent function? Some way that it would be easier to input it into my graphing calculator. How about, there you go. Great question. The inverse is not what you think it is. It's not the reciprocal. Yeah, that's unfortunate about our graphing calculators, that it looks like, oh, well, hey, you got the reciprocal right there. Unfortunately, it's not the reciprocal. It's the inverse tangent, which for us is going to mean something much different. So, but thanks for that suggestion, and thanks for the answer there. 1 divided by tangent of pi x, so second up arrow, pi x divided by 4. And there you go. Should be good on that. For the window, I don't think I need to go out this far. Let's go out to -8 to 8. And I'm going to have tick marks, you know, wherever I want them. But if I put tick marks every, let's see, every 2 units, that should be good. And then we'll stick with -10 to 10. That seems to be working out pretty good. We're in radian mode, so hit it. There's your graph. So it's not really as visible, but I guess I left out one of the vertical asymptotes, which is right here on the y-axis. This is also a vertical asymptote. It's just hard to see when you got the rest of the graph. But the graph kind of snakes through in a decreasing fashion. So let's draw that. Something like that. And that's 2 periods of the graph. If that's all I asked for, you could be done. I will draw a couple more. There you go. That's what I'm looking for. And your graph should go through the x-axis pretty much right in the center of your 2 vertical asymptotes. The domain is x is not equal to 4 times n, and the range is all real numbers, -infinity to infinity. Beautiful. How are we looking there? I'm hoping you're getting really good at this and feeling really comfortable. Comments or questions? All right, let's take a look at the chat here. Cotangent one? Sure. Yeah, let's do y equals the cotangent. Actually, you know what? Let's do negative cotangent of 1/3 x. Okay. Why don't you see if you can't make some headway on that for a little bit. Start by figuring out where this is in terms of its vertical asymptotes. So y equals negative cotangent of 1/3 x. So it'd be negative of cosine of 1/3 x over sine of 1/3 x. And I'll be quiet for a little bit, let you guys work on that. Help each other out, post questions in the chat, reach out to me if you have some questions. But this is your chance to see, do you know this stuff? How well do you know this stuff? And if you're watching this later, then you can fast forward until I pick up the pause button. don't think this one will fit very neatly on our graph. I don't think it's wide enough. You might have to relabel the x-axis. Okay, how are we doing? Can I get a few thumbs up? Are we doing okay there? Or you need another minute? All right, only a couple thumbs up. I'll give you another minute to work on that. Then we'll do the big reveal. Okay, let's work at this. See what we do. See what we can do. First of all, this is going to have problems when the denominator is equal to 0. Sine's going to equal 0 when this term in here is some multiple of pi. So how am I going to solve for x here? What do I have to do to get it? Yeah, multiply both sides by the reciprocal, 3 over 1. So 3 over 1, 3 over 1. That cancels. It leaves me with x equals 3n pi. So 3n pi here. For various values of n, you're going to get 6 pi, 3 pi, 0, negative 3 pi, and negative 6 pi. So our window, if you're going to do a couple of periods, is you need to be a little bit bigger. What I did on my graph is I just relabeled the x-axis so that this is all in units of pi. So pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, etc. So that way it gives me the proper width here. I drew in my vertical lines. As far as graphing this is concerned, what I would do is I'd write that as -1 over the tangent of 1/3 x. That should be good enough to give me my graph. So I did that on my graphing calculator. Let me show you the equation. I just wrote it as x over 3. That's the same thing as 1/3 x. My window, I set it up to be a little bit wider than what I had. So I went negative, let's see, no, I don't want that. So -3 and then pi. Now, as soon as I hit the enter key, that symbol will disappear and I'll get 9.24, etc. This is already at 3 pi. X scale. Can you tell me what I put on my x-axis for the scale? Yeah, units of pi. That way it makes it a little easier to read. And there's your graph. 1, 2, 3. So a distance of 3 pi, that's the period for this graph. So yay. And I've got 2 periods. I went from negative 3 pi to 3 pi. Now this graph actually kind of looks like the graph of a tangent because it's an increasing function. But the reason it looks that way is because you had a negative in the numerator that reflected your graph. So it's an increasing function as opposed to what we usually get from the cotangent, which is a decreasing function. So something like this here and there and so on. Did that help? You feeling better about these? All right. Thank you. Well, you can just look at the graph. You just look at the graph on your graphing calculator, right? I mean that's one way you can do it. I mean, back before everyone had graphing calculators, I would suggest people testing a point. But that seems to be much harder than what we need to work on now because you can just look at the graph. So that's what I would suggest, is just looking at the graph. Do realize that the shape of a cotangent is usually going to be kind of the opposite of this. So let me find my graph of the cotangent. Here's the graph of the cotangent. It's only when you flip this that you're going to get the graph that kind of looks like the tangent. Remember the tangent graph? Let's see. This is the graph of the tangent. All right, so it's an increasing function. It's when you multiply by negative that you get kind of that opposite effect. So you get a decreasing function. If you're going from the tangent multiplied by negative, you get the graph that looks kind of like the cotangent, and vice versa. So it's just being familiar with the shapes. So Crystal, what I would suggest is that you expect one of these two shapes, and then you can kind of confirm your intuition as to increasing function or decreasing function by looking at the actual graph on your graphing calculator. I'm not going to take away your graphing calculator on the exam. You will have that available to you, always. Okay, great question. Anything else to follow this up? All right, let's take a break.